It's hard to imagine the production of oil and gas without the use of high-quality products such as zeolites, those highly adsorbent and effective catalysts. Zeolites dehydrate air in truck braking systems, in control equipment systems, extract water from freon in air conditioners, and carbon dioxide from air in oxygen manufacturing plants. But most importantly, zeolites play a vital role in dehydrating and purifying natural gas, oil gas, liquid and gas flows at petrochemical plants. Zeolites are also known as molecular sieves. Due to their microporous structure, they can sieve molecules as well as selectively absorb or separate certain substances. Let's look at an example. Zeolites are regularly used in the production of double-glazed windows for the effective control of the level of moisture between the two panes. Since zeolite granules selectively absorb only water molecules, not oxygen or carbon dioxide molecules, the air between the two panes is easily dehydrated, without producing a vacuum at the same time. The result is a double-pane unit that, although airtight, does not deform when exposed to a temperature drop of the adjacent ambient air and produces no condensation. Thanks to zeolite granules, the unit is durable, has a long lifetime, and does not fill with condensation. In addition, zeolites are used in many complex chemical processes and are routinely applied in sectors such as construction, pharmaceuticals, and agriculture. KNT Group is a major manufacturer of adsorbents and catalysts in Eastern Europe. The KNT Group is made up of two plants: Sterlitamak Catalyst Plant, or SCP, and Ishimbai Specialized Chemical Plant of Catalysts, or ISCPC. KNT Group has been producing molecular sieves since 1985, thereby boasting a great deal of experience in zeolite production spanning a quarter of a century. We carefully examine each stage of zeolite preparation, invest in modern facilities, and choose the most effective engineering methods. Synthetic zeolites are produced in the form of granular extradates, which have different microcrystalline structures. The input window of the molecular lattice can vary in size from 2 to 15 angstroms, depending on what chemical process the zeolites are intended for. But their main purpose is the dehydration, purification, and separation of gases and liquids. Separating different molecules is achieved by altering the size of the input window. Depending on the size of the window, only certain sized molecules are adsorbed onto the zeolite surface. For example, water molecules are smaller than both carbon dioxide and oxygen molecules, and thus are easily trapped by a zeolite's crystal lattice 3 angstroms wide, whereas other molecules simply bounce off the surface. Synthetic zeolite granules have a system of secondary pores and channels through which gases can be percolated. KNT Group specialists measure these pores using special units. Surface analyzers are used to measure micropores and mesopores in the range of 0.8 to 100 nanometers. This method is based on zeolite absorption of nitrogen at liquid nitrogen temperature. A mercury porosimeter is used for measuring pores from 5 to 10,000 nanometers. Distribution of the secondary pores according to their sizes is very important. A dominance of small pores can lead to a choking of the pores by coke and to diffusive restriction, shortening the zeolite's lifespan. A dominance of macropores reduces the strength of the granule. KNT Group specialists managed to find the ultimate solution to this problem and a way to optimize the balance between different pore sizes. Zeolites as microscopic crystals in powder form before being molded into extrudate and granules. Zeolite crystals are grown in special solutions at high temperatures. The solutions are prepared by loading a mixture of different components in a specific ratio into a crystallizer. Seeding the solution guarantees the crystals grow in the right direction. The use of automatic devices eliminates error margins and guarantees high quality. Crystal growth is checked hourly. Specialists identify the zeolite type and can control crystallinity with the help of X-ray diffractometers. Additionally, crystal size is also monitored using Fritsch nanotech lasers that analyze particle dispersiveness. Each zeolite type has its own chemical composition, which is checked by a high-accuracy inductively coupled plasma mass spectrometer, or ICP-MS. The suspension thus obtained is then filtered when crystal growth has finished. Zeolite crystals are washed from the mother solution on Panavis belt filters. And then are dehydrated in drum dryers. That is the final stage in the production of zeolite powder. Theoretically, this powder should have a static water capacity of 25% at 100% crystallinity, which means that under certain conditions, the zeolite can absorb 25% of its weight in water. KNT Group specialists measure water absorption capacity at 25 degrees centigrade and a humidity of 10%. But zeolite powders alone are insufficient for use in gas drying. First, they must be converted into granules by mixing the zeolite powder with a binder. And subjecting the mix to high pressure. The extrudate now has a lower water absorption capacity of only 20%. Why is the water absorption capacity less? The answer is simple. The additional binder does not absorb water, it does, however, add bulk. Static water absorption capacity is not as important for synthetic zeolites as dynamic water absorption capacity. At an industrial level, zeolites are subjected to rapid streams of gas. Therefore, it is essential that water be absorbed quickly. For this reason, KNT Group specialists measure the dynamic water absorption capacity of each production batch. This is achieved as follows. First, a glass adsorber is loaded with a sample of fresh zeolite. Then a mixture of air and steam is passed through the adsorber at a set rate and the dew point is recorded. Measuring the absorption capacity of a standard zeolite with its binder, we may be surprised to find a capacity of only 13%. But why is this so low? To understand this, we must examine the extrudate further. Zeolite crystal channels are blocked by the binder, and water molecules cannot gain access from all sides. Blocking the crystal in this way reduces the molecular sieve properties of the zeolite. KNT Group specialists have solved this problem by using a novel manufacturing technique. Zeolite extrudates are formed using a temporary binder which disintegrates in a specially prepared solution, allowing new crystals to grow and combine with each other. thus producing granules that consist entirely of synthetic zeolite. Tests on zeolite granules produced in this way indicate a dynamic water absorption capacity of 22%, 1.5 times its previous level, and a twofold increase in strength. This new method of producing zeolites is of course more expensive than previous methods, but the advantages are evident. KNT Group zeolites are more efficient and can be used for longer than zeolites produced by other manufacturers. If the time taken to reach saturation is 1.5 times slower, then we have 1.5 times more time to use the zeolite before it reaches breakthrough, and your choice of high-quality zeolites is entirely justified. KNT Group zeolites are more attrition resistant and have a higher degree of mechanical strength compared with standard zeolites, where we observe crystal failure due to the constant heating and cooling. Zeolites manufactured using technology developed by KNT Group will increase the efficiency of your production process and help reduce costs. In order to obtain more reliable results, it is necessary to test the zeolite under conditions which are as close as possible to real conditions. For this purpose, KNT Group specialists have designed a pilot unit running under a pressure of 40 bar. The zeolite is then loaded into a metallic adsorber, and different mixtures of gases are allowed to pass through the adsorber: propane, methane, carbon dioxide, hydrogen sulfide, water vapor, air, and other mixtures depending on the objectives behind the test. Having passed through the adsorber, the mixtures of gases are analyzed using a gas chromatograph and various other analyzers. The gas breakthrough is fixed and the zeolite capacity for different gases is calculated. For example, carbon dioxide capacity is measured when air goes through zeolite 13X. This process is widely used for extracting oxygen from air. Zeolites are shown to absorb carbon dioxide only when it is present at a very low concentration. When we compare data obtained from the pilot experiment with how the zeolite performs at an industrial level, we can see that the pilot experiment effectively reflects real life. A huge amount of work over many years has gone into optimizing the technology behind producing zeolites. Thousands of different zeolite samples were synthesized and then subsequently tested using the pilot unit. Tests performed by leading companies in the field show that zeolites produced by KNT Group are among the best zeolites in the world. KNT Group specialists supervise every step of the production process and guarantee high levels of quality. Large investments into research and development in this area will be rewarded with great future results. Industries worldwide choose zeolites produced by KNT Group. Industries that place a high value on progressive technology. Call us today, and by tomorrow we may already be firm business partners.